today we have Toby Harris, and thanks very much for offering to do this, Toby. Toby's currently the director of space applications at HEO. HEO is developing novel space-based imaging capability. He's going to tell us about that today. But just a quick background bio on Toby. Before joining HEO, he worked at Astroscale as global head of space situational awareness, where he was responsible for making sure that the SSA needs for their current Astroscale's current and future missions. But he also then went on to be the director of government relations and space policy. And prior to that, he was head of orbital systems within the chief engineer's office at the UK Space Agency. So we have a little bit of a shared history there. So Toby, over to you. This is just really a kind of informal talk, but with an opportunity for people to ask questions afterwards, and we will try to end quite promptly at past. Could I please ask people, you're very welcome. It's nicer actually if you put your camera on, because then we know you're not just disappeared somewhere, but you don't have to, but please keep your microphone off. And if you want to put any questions in, I'm going to say to please use the Q&A function, but feel free also to chat amongst yourselves in the chat. Teresa's going to tell us if for some reason we can't use the Q&A function, but that's really the easiest place to put a question in if something pops up while Toby's talking and you want to capture it and not forget it. Toby, over to you.
Thanks, Catherine. Yeah, I'm excited to be here. Thanks for inviting me to talk. So I'm going to talk a little bit about HEO, what we do, some of the applications of the work we're doing, and some of the future work we're doing. So hopefully you can all see this presentation at the moment. Just shout if there's any problems. So who are HEO? We're actually a spin out from Australia's University of New South Wales. We set up in Sydney with our founders, Will and Hiranya, in 2019. And now we have a London office, which I'm currently sitting in, actually just outside MOD main building. And we also have a US office that recently opened in Washington, DC, late last year. Just closed a Series A funding round of $8 million very recently. And we're looking to grow and expand and see how the team develops. And our kind of motto is image anything in the solar system on demand, which is quite optimistic. We're going to start with LEO for the moment, and then we'll see how we proceed onwards from that. But that's the long-term goal, as it were. So what do we do? HEO performs something called non-Earth imagery. Now, non-Earth imagery, it's also known as satellite-to-satellite imaging, or SAT-squared, or space-to-space imaging. And basically, it involves the use of space-based sensors to capture resolved imagery of resident space objects. So that's not just sort of dots on a background or just sort of specks in the dark. That's trying to actually get multiple pixels of an object, a resolved image of something in space. And we're doing that using space-based cameras. So how does non-Earth imagery work? It's basically a type of inspection. And the way we do it is that we don't try and use a spacecraft to go and wander up to another object in space and take close-up images of it. There are missions doing that at the moment, and some of you might be familiar with Astroscale's ADRAS-J mission that was recently launched, which is doing exactly that, getting really close, taking some images of something. What we're doing relies on what's called opportunistic flybys. So we wait for existing spacecraft with cameras on board to come close enough to objects that we want to take pictures of, and then when they do, we take images of them. Now, Earth observation satellites are ideally suited for this. They have big cameras with small fields of view, and what we can do is we can take control of those for a short period of time. We can spin them around at an object that we want to take a picture of that's coming close enough, and then take an image of it. That doesn't require any fuel, so you're not limited in lifetime in that sense. It doesn't require us to move the satellite, do anything really, rather than just spin it around and point it in the right direction. Obviously, that relies on opportunities occurring. So we look for conjunctions between objects. Now, in the space safety community, obviously you're looking for conjunctions to try and prevent a collision. We quite like conjunctions because they come close to the things that we want to take a picture of. So the more conjunctions, the better in that sense. Obviously, the better the data we have, we can at least guarantee that we're not going to, collide with that object, but also taking a picture of something that's traveling a few kilometers away with a relative velocity of 10 kilometers per second with a sub-degree field of view is actually really challenging. So the better the data, the better it is for us imaging as well. Okay, so how does HEO do NEI? Now, like I said, we want to use Earth observation satellites because they're up there at the moment. So the way we do it is we access Earth observation satellites. We talk to the suppliers of these satellites, and we set up an API. We set up a software link that enables us to directly command those satellites for a short period of time. And we start at number one in the bottom left-hand corner there. We have this software called HEO Inspect, which is actually just an online portal. You can type in your NORAD ID of what object you want to image. It would look for the nearest opportunities, sort of the conjunctions that are coming up in the next week or two. It would work out what the best opportunities are, and then you press go, and it would send that up to the satellite, and then hopefully in a few days it will take an image. Once that image is taken, it will come back down to this HEO Inspect portal, where our team will process it, extract useful information, images and data, and then send them back to the user. So what's our current coverage? Now, Earth observation satellites are predominantly in LEO. In fact, they're all in LEO. So our current coverage is very much limited by where those satellites are. So we cover about 2/3 of LEO at the moment, where most of the Earth observation satellites we have access to, and I've mentioned a couple there, Axel Space and Satellogic, are in the sort of 500-kilometer region, which means that anything sort of above and below that region by a couple of 100 kilometers are what we consider in coverage. Now, what we'd like to do, and I'll speak a little bit about this later on, is look at coverage of different regimes as well. Currently in GEO, there's no Earth observation satellites. There's no satellites that have access to this kind of, or at least carry these kind of payloads that we need to do this. But that's something we hope to change in the future. So at the moment, we're currently limited to about 800 kilometers in altitude, but that still covers a huge number of objects in LEO. Okay, so what does NEI look like in action? Space stations. The ISS is a great object to try and image for NEI. It's nice and low down, it's nearby to the Earth observation satellites that we use, and it's a great big target. So we've imaged the ISS many, many times, really to help calibrate our sensors and to try and improve the ability for us to actually image objects. And what we do is we actually reconstruct the objects we image using 3D models as well. And that's a great way of trying to extract useful information about them. We can build the 3D models, and then we can use the images to add things like dimensions to them or add features that perhaps we didn't originally have. And the ISS is a great way of doing that. You can also see that this is taken in not just one band, these are actually multiple bands. You've got near infrared on the left, you've got green in the middle, you've got blue onto the right there. And so we actually take them in multiple different bands, and occasionally we're able to combine those to create color images as well, or some interesting ones in sort of infrared. Now, the Chinese space station is actually an interesting one. We sort of consider this a pattern of life application. What we did is we imaged the Chinese space station from the sort of heyday of HEO just coming about, so a few years ago. And we tried to take images regularly to try and understand how it was built over a period of time. And in doing so, we also reconstructed the space station using 3D models to sort of explain how it was built. The Chinese space station is currently, it's obviously operated by the China National Space Administration. It currently features about 3 permanent pressurized modules occupied by a crew of 3. And we imaged how it was built, all the different components over that sort of 2 to 3 year period. What we really need at this point is some sort of epic music as this thing gets built. It feels a bit weird at just being silently constructed there. And you can kind of see the features as they appear on the imagery, and how that kind of matches the 3D model that we then base on that. And here we have sort of the final images, a couple of color images there. And then you can see this last one where they've actually tilted the solar panels, and you can see the little command module. Okay, so space stations are fine, but what about things that are of more interest to us, things that perhaps we actually want to image? Rocket bodies and upper stages are of particular interest. It's well known that these are some of the largest objects in orbit and pose the most risk because they're not normally controlled. They're basically just waiting to slowly deorbit. And so we've been looking at imaging a lot of these to try and understand their state, as well as trying to identify what they look like and whose they are even. As well as upstages, we're able to image satellites, obviously the most populated object in space, both inactive and intact derelict objects in space. And we can do that for a variety of reasons, which I'll go to in a second. And you can see again that we can use these images to try and then recreate 3D models based on what we're taking images of. So those are a couple of images that we've been able to take. What about the applications of NEI? How can you actually use this? So one of the key applications is object identification. At the moment, there are so many spacecraft going into orbit at the moment, or so many objects, it can sometimes be very difficult to identify which is which. There's a number of rockets that go up at the moment where multiple objects, 10, 15, even 20 objects might come off of it. And it can take days, even weeks, to identify what they are, who they belong to, and so on. And so one of the applications that we're using at the moment is fast object identification. We can take images of everything that comes off a bus within just a matter of days, and we can quickly identify what they are. And these are a couple of images taken of some unknown objects that were released from a foreign rocket. And we were quickly able to identify what they were and a few features about them as well. How many solar panels they have, the size of the bus, these kind of aspects are all useful information. Mensuration, again, another bit that's very important for a variety of applications. Mensuration is basically the act of measuring the geometry of an object, computation of lengths, areas, volumes, all that kind of thing. And when it comes to trying to understand, for example, the capability of a spacecraft or an object, you want to understand the dimensions of it. So you might want to understand the size of the solar panels, what's its power generation, the size of the antenna, what's its bandwidth, what's its range, what's its capability, and then also looking at the payloads as well. What are those kind of based on the size of the payload or the size of the aperture, what's its capability? So these are all really important things to be able to gauge. And you can do a certain amount from getting radar cross-section, for example, but when you want to get details, it's much better to actually get a resolved image. And even a low-resolution image can provide useful information for some of these unknown objects. Tumble rate assessment. Now, tumble rate assessment is really important in a variety of applications. And actually, tumble rate it's actually sort of two parts. So tumble rate is just identifying whether something's tumbling or not, or whether it's stable. It's almost sort of like a yes-no question. You've also got attitude rate assessment, which is actually understanding how an object rotates, how fast it's rotating, what axis it's rotating on, and all those more detailed aspects. Tumble rate is a little bit easier. You can take an image of an object over several orbits, and you can actually work out whether it's stable or not. Whilst if you want to do tumble rate or attitude rate assessment, if you want to understand how fast it's spinning and what its axis is, it's a bit trickier, and that requires taking multiple images over a short period of time, often during a single imaging opportunity. Now, one of the ways we're looking at doing that is by what's called slewed NEI. So typically the way we take images at the moment is we point the camera in the direction that we know the spacecraft or object's going to pass through. And when it comes through, we take a very quick image of it, sort of millisecond type exposure time, and there we have an image. Now, if we're lucky enough that the relative velocity is very low, so the orbit of the imaging camera is very similar to the object that we're imaging, then we can actually get multiple images of it over a period of time. And you can see that illustration there in the bottom left. We've got multiple images of the same rocket body. And if you image it over enough time, say tens of seconds or a minute, then you can actually start getting information about how it's moving in space relative to the camera. Now, this is obviously very difficult, and there's very few opportunities that enable us to do that. Another way of doing it is to actually move the imaging sensor, the satellite itself, so that it's constantly looking at the object we're imaging as we pass by. This is what we call slewed NEI, and it requires the imaging spacecraft to slew as it passes. And it's very complicated. A lot of the Earth observation satellites that we use weren't designed for this. So it takes a little bit of ingenuity in order to do that. We have done it several times, and it's actually going to become our standard concept of operations for imaging in the future. Because not only does it enable you to take multiple images, it also deblurs the images a lot. And you see some of the images we've taken so far have been quite blurry because of the relative velocity. We're hoping that this slewed NEI approach is going to remove a lot of those issues and actually enable us to get crisper images and also multiple images. So supporting active debris removal. There's several aspects that you need to know when you do active debris removal about the client or the target or whatever you want to call it that you're trying to remove. Now, for those of you not familiar, active debris removal is taking your spacecraft to go and remove a defunct object that would take too long to deorbit on its own. There are some companies and organizations looking at this at the moment. We have ESA at the top right there, looking to try and remove Envisat or some of their other large objects. We also have Astroscale and ClearSpace at the bottom there. And they're looking at using these spacecraft to try and grab onto or capture these objects and then actively remove them from orbit. Now, if that object that we're looking at is spinning very quickly, if it has solar panels in awkward positions or a gravity boom that isn't there or something like that, then that means there could be complications in trying to remove it. So it's very prudent to try and know as much as possible about these objects before you actually commission a spacecraft and send it up there to remove it from orbit, because you don't want to get there and realize that your spacecraft is not equipped to remove it because it's spinning too fast or there's no capture points, etc. So this is one of the applications we would like to explore for non-Earth imagery. And rather having to have a dedicated inspection spacecraft, we can simply survey all the objects up there over a period of time and come up with this information, almost like a database of data that we can provide to say which of these objects is most appropriate for ADR. And then for mission specific as well, we can actually look in more detail about how you could capture it, for example. Re-entry. Many of you might have seen the recent re-entry of ESA's rather large ERS-2 spacecraft. We actually did a short project with the UK Space Agency, funded by UK Space Agency, to try and image this spacecraft as it is re-entering. And we managed to image down to about 300 kilometers. You can see that graph there that shows the re-entry trajectory, and you can see the images and when they were taken. One of the bits of interest here is to try and understand again the tumbling motion of it as it re-enters, because that really does affect the drag area and the trajectory that it re-enters. And so one of the ideas is if we can get a better characterization of how it's moving, what its time-dependent drag area is, we can perhaps improve the prediction of re-entry in terms of where it's going to re-enter, the time of its re-entry. This is something that we're still looking at as very much an R&D. 300 kilometers probably isn't quite low enough at the moment to try and get sufficient useful quantitative information to try and improve re-entry prediction. But we'll be looking at having lower satellites that will be able to do imaging at much lower altitudes in the future. And so this is something we're really excited about, trying to explore whether we can use non-Earth imagery to better characterize re-entering objects and improve potential predictions and where it might re-enter if it doesn't demise in the atmosphere. Okay, and the last one on the applications here that I'll talk about is licensed supervision. Once a spacecraft is in orbit, from a ground-based point of view, you can only really see it as a dot on the background moving around. You can obviously see where it's going and potentially what it's doing. But what NEI offers is a non-intrusive way of observing certain missions or certain activities, which could be used for a supervisory role under various regulatory frameworks. And here we just have a couple of images here of one of the applications, rendezvous and proximity operations, where two spacecraft or a spacecraft and another object come close to one another. I've already mentioned this in terms of active debris removal, but in the future, there's going to be a lot more potential situations where you can get two spacecraft close to one another. In orbit servicing and manufacturing has a wealth of different types of missions that might require that. And we've shown that we've been able to capture two objects in the same frame when they're within just a couple of 100 meters. And actually at that point, it's very difficult to understand what those two objects are doing using ground-based sensors. It's hard in LEO, it's very hard to do in GEO simply because it's too far away. So NEI will potentially offer an opportunity to see what's going on at those very close ranges. Okay, and I briefly mentioned Inspect earlier. This is what our platform looks like. When customers have accounts with us, they'll be able to task satellites, effectively type in your NORAD ID, see what opportunities they are, task them, and then within a period of hours to days, depending on the opportunities that are available, you'll be able to get images, insights and analysis, as well as potentially models and database access as well. Okay, just a little bit about some of the other things we're doing at the moment. Now, I mentioned before that we're very much reliant on Earth observation satellites in low Earth orbit. What we'd like to do is have cameras elsewhere as well. We want to cover the whole of LEO. We want to cover GEO. We're thinking about MEO, but MEO is challenging because inclinations are all over the place and it's quite big. So LEO and GEO are obviously very important to us, and then potentially cislunar in the future. But in order to do that, we need to get cameras on buses, and we need to get them in orbit. Now, here we're probably not going to build our own spacecraft, but what we are doing is building our own cameras, which are designed specifically to support non-Earth imaging. And so there's a couple of examples here. Holmes on the left and Adler on the right. They are, if I remember, 4-inch and 8-inch respectively cameras. And we'll be looking to build bigger ones in the future. And we are currently looking to get those hosted on platforms. We already have 2 in orbit at the moment. So Turian Droid satellite was launched by SpaceX Transporter 8 in June last year. And that's currently being used at the moment. I believe it's still undergoing testing. And then Holmes 2, which was launched on a Space Machine satellite, again on a SpaceX Transporter 10, that was launched early last month. And again, that's just been undergoing testing at the moment. And so hopefully we're going to have both those spacecraft testing our ability to use Holmes and to do non-Earth imagery. And in the future, we'll be looking to expand our coverage even further. So these are just a couple of graphs to try, or a couple of charts to illustrate our sensor coverage and sensor types over the next 3 years or so. We're hoping to get, by early next year, several satellites in VLEO, denoted by the blue bit on the left-hand graph there. And that will enable us to do things like improve our re-entry observations. We're also looking to get our first satellite in GEO early next year. And that'd be really exciting because there's been no commercial capability to image anything in GEO before. And so we're going to hopefully be using that with our larger camera, with Adler, to start imaging objects in GEO and also in Graveyard as well. And then in time, over the next few years, we'll be expanding both those areas to improve our LEO coverage, to improve the frequency of imaging and the fidelity of imaging in LEO, as well as to add new capabilities in high LEO, very low VLEO, sorry, and also GEO as well. And then on the right, we're also looking at trying to expand the types of sensors we have on orbit. Most of our sensors at the moment we rely on are optical with near infrared. We're looking to expand that to look at thermal, so full infrared. The idea there that we can then start imaging things in eclipse, so we don't have to worry necessarily about the sunlight, and that opens up a wealth of new opportunities. I'm also looking at UV, hyperspectral, and also SAR as well. So it's been shown before that SAR imagery can, or SAR rather, radar can actually create images. It's been done on the ISS, and we're looking to do exactly the same thing to try and use some of the SAR commercial satellites and try and gain imagery from that. That's something that actually really works in our favor because of the high relative velocities involved. That actually works for SAR to help get the image that relies on relative motion. It just requires some rather high frequency radars in orbit. Okay, and I think that's pretty much everything from me. Just in summary, we at HEO, we're performing non-Earth imagery, a unique approach that uses Earth observation satellites at the moment. to collect space situational awareness data. So we're using EOS assets to do SSA effectively. Our platform, HEO Inspect, enables end-to-end tasking, imagery, and analysis. And we have this broad applications to both civil, defense, and commercial use. And we're hoping that our capability will grow as our partnerships expand, we get new sensors added to the constellation, and our software tools improve. And that's us calibrating the sensors using the moon. So we managed to get the moon initially.
Thanks very much, Toby. Does anybody have any questions? I know I said we'd finish promptly at 12:30, but that was such an interesting talk. If nobody's raising their hand, they're going into chat. That's fine. Did you, R2, did you want to ask it directly? Well, to save time, R2's asking, do you have data imagery available for academic purposes for universities? Oh, and his mic's, whatever, their mic's not working. So they're a defense researcher, and they're asking if you have data imagery available for academic purposes for universities.
So at the moment, you can see at the bottom there, we've got our HEO Robotics Inspect sign up. So you can get all the imagery and data we have on the International Space Station. Obviously, as a defense researcher, that's perhaps not as much of interest, but I think that will give you an idea of the kind of data that we can provide. What I'd do is encourage you to get in touch directly, and we can talk about the kind of imagery that we might be able to provide for research and academic purposes. And I think my email's up there.
Great,
so
thanks, Toby.
Send me an email.
James and then Duncan.
Hi, Toby. Thanks for that talk. I had a quick question about, do you ever find that objects aren't where they're expected to be due to sort of uncertainties in orbital states and so on? Is there ever kind of cases where, you're pointing where you expect it to be and you get the image back and there's no object there, or anything along those lines? I imagine when you come to sort of image debris down the line, small debris and so on, as we get better at discovering that, will that be kind of a major challenge to overcome? Thanks.
Hi, James. Yeah, absolutely. We do miss. And a lot of this is down to the quality of the data we have on an object. And actually with ERS-2, when it was becoming really low, 300 kilometers wasn't really the range of our telescopes. It was because the data we were using became so uncertain, it was quite hard to take an image of it. It kept on going out of frame. So I think what we need is really good SSA data. Now, originally we were using TLEs. Since then, we've been using SP ephemeris, and we're also looking at, for specific objects, using operator ephemeris. But the better data we can get on the object, the more chance we have of getting it first time.
Mm-hmm. Thanks.
Thanks. Duncan. Duncan?
Yeah,
Hi.
I'm here. Right. Thanks, Toby. That was really impressive and interesting. I was just wondering, and you may have said this, but you covered a lot of ground, so I might have missed it. Have you looked into using your sensor as an additional sensor on debris that would otherwise perhaps be hard to get an orbit determination for on the ground? So this is not necessarily looking for a polar crossing to with which to observe a specific other satellite, but just switching the camera on and seeing what there is there.
I mean, we have thought about that. We thought about doing things like tipping and queuing, so using our imagery to improve the ability to acquire an object using ground-based sensors. I think part of the problem is that we do have a very small field of view, so it's not really set up for just sort of sitting there and waiting for things to come through. It's quite difficult to do that. And also, these are Earth observation satellites that are used for taking pictures of the ground for the most part. We normally use them when they're passing over the sea, so we don't have access to them all the time. We have access to them at specific periods of time. Normally we'd task it for a minute window or something like that in order to take an image. But so we don't have access to it in a continuous fashion like that either. So certainly we thought about how we could use it in that for that kind of application, but it's not something that we've continued with at the moment.
Okay. And just to cheekily get another question, and it was quite interesting you mentioned over the sea. I was presuming that you were looking for availability over the poles. One, because that's where you'll get conjunctions with other spacecraft, and then two, because a lot of Earth observation spacecraft will be used less over the poles. But it's quite interesting to see looking over the sea. So does that mean effectively you have, well, in principle, access to do imagery at any latitude?
Potentially, yeah. It does depend a little bit, and you're probably right that over the poles there's less interesting stuff to image on the ground, and there's more conjunction opportunities with other polar or SSO satellites or objects. But yeah, we still, because we're imaging over the sea, we can still take pictures of things that are in equatorial or non-polar orbits.
Great, thank you.
Thanks, Toby. I'm going to take Diana's question as the last question. Diana? Oh, we can't hear you.
Sorry.
Yep.
Thank you so much, Catherine and Toby. Fantastic presentation. One quick question. The database that you were planning to create with all these images you have, is that like a service, like an extra service you will be selling to, I suppose, like a military and other like defense or other stakeholders, or is going to be like a free database?
Hi, Diana. Yeah, it's a great question. It's something we've talked about, but I don't think we have a clear answer on that yet. You're right, we're building up quite a big database of imagery, of data. It's not free available at the moment, and we're having those discussions at the moment of how we perhaps want to use that, what the interest is from potential customers. So I think that's a case of sort of watch the space, and we'll see what happens.
Okay, thank you.
If you have good ideas for potential customers, you should get in touch with Toby, Diana.
Absolutely.
Okay, well, thanks everybody for joining us. I'll just say as I said, keep an eye out on the GNOSIS newsletter and the website for further one of these GNOSIS Connects. We have a couple in the pipeline, and also just to flag up that our next conference is in the planning stage now, and to please hold the dates in your diary for November 12th and 13th. We hope you'll be able to join us for that one. And it just lastly to say thank you very much, Toby. That was so interesting. I had a bunch of questions, but I will catch you the next time I see you to ask those. Thanks, everybody, and have a great day.
Cheers. Thank you very much.